wave AC is either
Or it's,
a pulsating DC.
it's AC. Full wave is
Sorry.
into pulsating DC, right? And then what's our filter supposed to do?
To change unregulated DC.
Yeah, change it to unregulated DC, and what does that mean?
Change the varies with the load or it varies with the input.
Yeah, it varies. If your input changes, if your input voltage changes, the output will change. If your load changes, the output will change. So, yeah, you can unload that thing and you can put a capacitor on that sucker, and it'll be perfect DC. It'll be beautiful. As soon as you put a resistor load on there, the output's going to drop down, and then you'll see that ripple voltage. So the primary filter in a linear power supply is capacitors. They replace the capacitor in parallel with the load resistor or the output of the power supply. We're using load resistors, but you got to understand we have what we call dedicated power supplies that are designed to run something all the time, and then we have power supplies where we can hook our own loads up to them, right? You understand? So like the power supplies on the trainer, those are not dedicated power supplies. You hook up whatever you want to them. As long as you don't exceed the parameters of the power supply, then it's okay. So we'll probably need to look at that and make sure we don't do that. For positive power supply, during a half cycle, the capacitor charges, and this would be true during a negative power supply too. All we do to change from a positive supply to a negative supply is on the half wave and the full wave center tap is just change the orientation of the diodes, right? On a bridge, you just hook it up the way you want it, because the ground is established on the output of the diodes or the common. On a half wave and a full wave center tap, the common is established at the transformer. So since the common on a bridge, since the common is established on the other side of the transformer, on the other side of the bridge, you can, it depends on how you hook it up, right? So if you make your negative common and use your positive for your hot leg, then it'll be a positive power supply, but you just as well could have made what? The positive common. And then add a negative power supply. So that's why when you see an integrated bridge, it don't label common, it just says what? AC, 2 leads are labeled AC, and then 1 lead's labeled what? Plus, and the other one's labeled minus. So what's happening is when, as soon as your AC drops down, and so if we're looking at a positive power supply, this is pretty good. So as soon as the AC hits peak, so we charge during this time right here. Now this initial charge is going to take a lot of current. Y'all understand that? It's going to take a lot of current. And so where does all this current come from? Well, it's got to come through those diodes. The only thing that's limiting the current flowing into the capacitor when we charge it is the resistance of the transformer. And transformers have very, very little resistance. So that means we get a really big surge current. Don't really hurt the don't hurt the transformer because it's only there for a half cycle, right? Not even a half cycle. It's only there for that first 90 degrees, right? The diodes, though, this is where we got to watch out. So if you look at the data sheet for the 1N 4000 series, which is what we're using, right? Then we look for what we call the surge current. And the surge current for the 1N 4000 series is 30 amps. That's for 1/2 cycle, but we're not even doing 1/2 cycle, right? We're doing what? I think it's 1/2 cycle. Let me look at it. For a 1 whole cycle? Yeah. So a cycle would be, right, so 30 amps, and we're not even doing that. So this guy here has no problem charging that capacitor up. Now once the capacitor is charged up, then it never fully discharges if we choose the capacitor the right size. Does that make sense? So let me bring up the data sheet so it's recorded. So looking at these data sheets, this is very important to read. And so what we have is, I'll show y'all where they're at. Most of the time y'all get them, but we have the data sheets here on Blackboard, right? And then when we take tests, what we do is we give out a booklet, a loose leaf booklet that's got all the data sheets in there. We'll get those to you. So this is the 4000 series. Goes from the 4001 through the 4007. And what varies between the 4001 and the 4007? Y'all remember? So look, everything down in here is the same. What varies is this up here. That PIV, that reverse breakover voltage. So the 4001, which is the one most of y'all are using, is 50 volts. And then the 4007 is 1,000 volts. So Brandy the other day, she was looking for a 4001 because that's what the lab called for, and she had a 4007. And I told her, well, the 4007 is great, right? Because we're only using a 12.6 volt transformer, right? So 50 volts would be fine for the breakover voltage there. But a 4002 would be fine, a 4003 would be fine, a 4004 would be fine, because the only thing it changes is the watt. Breakover voltage. These are all 1 amp diodes, but non-repetitive peak surge current. 30 amps for 1 cycle. We're only charging it up less than half a cycle, right? So this guy here has no problem charging up that little 100 microfarad capacitor that you put in there. So you okay? So we're concerned with this. What's 1 amp? Can y'all read that? What is 1 amp? Yeah, that's your forward current, right? So average forward current. So as long as we run an average forward current that doesn't exceed 1 amp, this guy here is fine. So this would work real good in a 1 amp half wave. It would work fine in a 2 amp full wave. Because remember, on a full wave center tab, it's only conducting for 1/2 cycle, right? So if you did it says average current, right? So this diode's cut off for 1/2 cycle. So if we pull 1 amp when it's full cycle, then 1/2 cycle is going to be, so we could get at least a 2 amp power supply. And that would also be true for a full wave bridge. So you could get a 2 amp supply using 1 amp diodes, because they're what? They're off half the input cycle. So, and it says average, so y'all need to storage temperature. The VF on the thing should be anywhere between what? And this is at the rated current, by the way. So if we're running below 1 amp, which we would, then it could be all the way up to 930 millivolts, typically 930 millivolts, but it could actually be all the way up to 1.1 volt. And that's if it's running at its maximum current. Y'all not seeing that because we're not running these things near their maximum current. This is the average voltage drop running. This is instantaneous. I'm sorry. This is what? Yeah, so this is not really that interesting to us right here. This guy right here is, this is running at what? 1 amp with 1 inch leads. The people don't understand, the longer you make the leads, the longer it takes the diode to dissipate its heat. So if you look at a chart, especially on Zener diodes, because they run reverse bias and they get a little hot, they dirate depending on the length of the leads. So the longer the leads, the less power you can get out of them.
You think there'd be lots more surface area?
Well, you're dealing with the surface area of the leads and the surface area of a trace on the circuit card. Does that make sense? And the trace on the circuit cards are a lot easier to get rid of and to dissipate the heat than the watt. Also, the traces on the circuit cards are usually copper. The traces on the diodes are copper plated. They're plated with usually nickel or tin. And why do they plate the copper leads on the diodes? So when you look at your diodes, they're not nice and orange shaped or brass colored like copper. They're silver. And why is that? Why do they plate them? Yeah, it reduces oxidation. So you don't want to file those leads off because you'll get down to the copper, and then the copper oxidize and get into your solders. And plus, tin coating or they do tin sometimes, they do nickel. It also solder adheres to those metals better than it does copper. So it's actually easier to solder to tin. Then we have our reverse leakage current. So the maximum reverse leakage current, the maximum at 25 degrees centigrade would be about 10 microamps. At 100 degrees centigrade would be about 50 microamps. And then the average would be what? Yeah, around 30 microamps. So that would be the leakage current. And that'd be about all that we needed. And like I said, you can see the this looks like this might be the dye rating chart right here. No, I'd have to look at it. So for what we're doing, these diodes will work good. These will work good in a lot of different power supplies, but if you're going to use a higher wattage power supplies, then you're going to have to go to bigger diodes, right? I need to get the capacitor quickly charges at the beginning of the cycle and discharges through the load after the peak. So as soon as that sucker drops down past peak, the diodes cut off because now they're reverse biased, right? You understand? Because the capacitor is, the output of the capacitor is more positive than the input cycle. You understand what we're saying? So the diodes cut off. And how long? Then the diodes cut off. So right here, this is on the cathode, right? You understand? So as soon as this drops down, now the anode is negative in respect to the cathode. So what do the diodes do? They cut off. And how long do they stay off? So now we're actually running, what's running the load right here? Yeah, the capacitor's running the load. And then it gets down to here, and then what does it do? Then when the next alternation comes back up, it does what? It charges back up. And of course, so full wave at 60 cycle, we're going to have to size the capacitor to run the load for 16.7 milliseconds. And for full wave, we're going to do 8.3 milliseconds. And all you have to do is just take that formula and rearrange it and say, okay, this is how much ripple voltage I want, right? You understand, at this current, and then solve for C. And then you can size your capacitor. And always do what with it? Go higher, yeah, at least. And this is what they're showing you. That's why we use that formula, because my DC average is not up here. My DC average is not right there. My DC average is where? Down the center, because it's a repetitive AC waveform. And if you got a repetitive AC waveform, your average is going to be right in the center. No matter whether it's a sine wave or any AC waveform is going to be in the center, right? You understand that? But here we're riding it on top of DC. So this is something we're going to have to get used to in solid state, that we can superimpose an AC signal on a DC source. And if you don't understand that, then you're going to have trouble with bipolar transistors, because this is exactly what we do on those guys. So that's why when we calculate our ripple voltage, so what's the formula? Anybody got it on top of their head? So V ripple peak to peak, and this is a guesstimation, but y'all have noticed it works out really well. So V ripple peak to peak would be equal to what? Yeah, I of the load over the frequency of the output, not the input, times the size of the capacitor. So C would be equal to I over F V ripple peak peak if you wanted to solve for a capacitor for your power supply. So you say, okay, this is how much ripple voltage I want. This is what I'm designing my power, my transform. This is what power I need on my output or my current, and then solve for C. And just do what? Make sure you go up to at least the next standard value, unless it comes out to be perfect, and you still go up to the next standard value. And then our DC average is going to be equal to what? It's going to be equal to V peak out minus V ripple peak to peak that we calculated divided by 2. Because why? When we calculate this, we're calculating peak to peak, but where's my DC average at? It's down in the center, right? And that's where those formulas came from. Now, when we regulate, we're going to regulate, our regulators are going to regulate down in here. Does that make sense? So when we get a regulator, our unregulated has got to be more than what we're trying to regulate at. And then what we do is we regulate. So, you know, if this was a 5-volt regulator, that means it's going to be looking at that, which is really nice, good at DC, right? Does that make sense? But we're going to have what maybe? We might have to have at least 7 volts unregulated down here to do what? For our regulators to work. And now you got it. That's about all there is to designing one of these things. So if you wanted a 5-volt supply, you'd probably buy like maybe a 6.3 volt transformer. That would give you almost 9 volts out. And then you would regulate it down to 5 volts. And now you could have a pretty good deal of ripple up there. So here's our formula. This is the one I like to use. Because on this one, you have to figure out the time. That's where you'd use the 16.7 for half wave and 8.3 milliseconds for full wave. But here, all you got to do is know the what? The frequency of the output pulses, not the input pulses, the output pulses. This is what I'm talking about. In a rectifier circuit, if a capacitor is connected in parallel with the load, the capacitor appears as a short circuit at the instant we close the switch. So when you calculate your transformer fuse, what you need to do, you need to make sure you get what we call a slow blow fuse. Why? To allow that capacitor charge up, allow that surge. If you get a fast blow fuse and you size it right at what it'll get it. So get you a slow blow fuse. If the standard, these guys right here, I don't forget what they're called, the long ones, it would be an MDL. The little 5 millimeter, I don't know if they give it the MDL prefix or not. So fast flow fuses are AGPs. AGP, AG, AGP, I think. It's AG something. By the way, I've never seen this before, but the book, this book taught it, is that sometimes they put, this would be a real small resistor right here. To do what? Yeah, limit the surge. Normally we don't have to worry about that because the resistance of the DC resistance of the transformer is enough to limit enough not to cause any problems. It's only for the first 90 degrees. That's usually not going to hurt. I've never seen it hurt a transformer. I've never seen it hurt a diode, as long as you size them correctly. And if you use an MDL fuse over on your transformer, it's not going to blow the fuse. IC regulators produce a near constant output over a range of input voltages and output load currents. Typically, your IC regulators will have 3 terminals. You can furnish constant outputs, or you can make it variable. And what we'll look, I don't know why this figure shouldn't be on there. This is out of another book. The standard series of fixed regulators are what we call the 7800 regulators. These are positive regulators. You have the same ones in the 7900 series, which this textbook didn't cover. So we have a 79XX. These are negative regulators, and the 7800 series are positive regulators. And then the last digits tell you their regulated output. So a 7805 is a plus 5 volt regulator. A 7806 would be a what? 6 volt regulator. 7812 would be a 12 volt regulator. And this is the same thing true with the 7900 series. But these are fixed. You can get them in different current capabilities. You know, we have the L70L, 70LOH, RB. Those are low current. I'd have to look them up too. So you can get them in different. These standard packs. These guys right here are called a. I forgot the designator. 220 TP, no TP. I'll have to look at that. I think it's TP. I'll look it up though. And I'll give y'all when we get to transistors, I'll give y'all a printout that shows y'all the standard packs that these things come in. But see, they come in all sites and shades. They're all 5 volt regulators, but depending on which one you get would depend on your output current capabilities that you're going to regulate at. And it's a very simple circuit. You need this one. This is usually on the, I forgot. I'll have to look this up too. You can look. I think the 7800 series of regulators. I think I've got those up on Blackboard, and it would tell you the size of this post filter right here. And this is required depending on how far you're away from your main filter. These guys are really easy to do. 3 terminals. One side is for what? Unregulated in, and then over here is what? Regulated out, and then you have common. That's all there is to it for these things. It's very simple to hook up. You see these things used all over the place. In fact, these are what our trainers use for the +5, -5, +12. This is the actual regulators they use. They use the 7800 and the 7900 series for those. Really? So think about it. Okay, I need a 1 amp power supply, 5 volts. I try to get 6.3 transformer, 1 amp. Then I would make sure my transformer can handle 1 amp right on the output. Calculate my ripple frequency, my ripple, the size capacitor I needed to make sure when I'm pulling my maximum current, that thing doesn't dip into the regulated voltage. That's pretty much what it is. So these guys are real easy to design. If you're working with digital, though, you'd say having a 5 volt power supply would be really good. This is basic makeup. There it is, 1 microfarad. Here they're using 1,000 microfarad. Of course, this is going to vary with your current, right? And of course, this will vary. Odds are we wouldn't use a 12.6 volt transformer. Can somebody tell me why? So let's calculate what this guy right here is going to have to drop. So I'll come over here and I'll say V peak would be equal to 12.6 divided by 0.707. What's that? $17.8. Oh, then my V peak out. So this is V peak. My V peak out would be equal to 17.8 minus 1.4. 16.4. Okay. Now, this is pretty much well going to be V peak, right? The only thing that's going to be different is ripple. So what I'd have is I'd have 16.4 volts DC on this side. I'd have 5 volts on that side. So how many volts would my regulator be dropping? Okay, so 11.4 volts. So that's if it's 1 amp, that's 11.4 watts right here. That's just wasted power. So my regulator would get hot. We start soldering at 25 watts. I don't know if y'all have ever touched little light bulbs, even small wattage light bulbs, 30-watt light bulbs. If you put your fingers on them, they're going to do what? Incandescent bulbs, they're going to what? They're going to burn you. So this I wouldn't use a 12.6 volt transformer on a 1 amp supply, because this guy here is going to dissipate that. It's going to drop that much voltage. Power is equal to what? V times I. So power would be equal, if this is a 1 amp regulator, it's going to be 11.4 times 1. So power would be 11.4 watts. Doing what kind of work? Making the inside of my power supply nice and warm. So you choose your transformer, a 6.3 volt transformer would basically give us about half of that, right? So what would that give us? 8.9. So now we got 8.9 on one side and what? 5 on the other. Now we got ripple on the top of it if we choose our right capacitor, but still 8.9 volts peak to peak is still really good to get a 5 volt regulator, right? We can still have a pretty good deal of watt. We can still have a pretty good deal of ripple. So yeah, that would so that's something you got to make when we start dealing with these linear power supplies. These guys right here they got to drop the difference between the what? The regulated and the unregulated. I'm sorry, other side. They got to drop the difference between the regulated and the unregulated. And if they drop a voltage and you push current through them, they're going to do what? They're going to get hot. So what you're trying to do on these linear power supplies is make sure you use the right transformer. Either that or suffer or, heat up your and these guys here, by the way, have thermal detection circuits in them, so you can't hardly burn them up because they'll shut themselves off if they get too hot. This is another neat guy. This is an LM317. An LM317 is a variable regulator, and this is what I've got on my power supply. Now this is what's in the power supplies inside the trainer. Now there's a lot of electronics inside these things. I mean, you can look up a 7805 and there's a lot of electronics in there. But I'm not concerned with what's inside this guy, because if something goes bad, what do? I replace the whole thing. So right now we'll look at a little bit on how these things work, but I'm not concerned. But notice it has an in in it, it has an unregulated in, it has a regulated out, and then we have a bridge right here. I'm sorry, we have a voltage divider right there. And what this guy does is it maintains, this resistor right here is always going to drop 1.25 volts. So if I raise this and try to make this voltage go up, then my output's going to automatically go up to maintain that watt. That 1.25 volts, which is pretty neat. So this would be a pot, usually it's a pot wired as a rheostat. And these guys here are great. I mean, they're real easy to work with, real easy to design around. I'll try to give y'all what you need to do on this. It all depends on the power rating on your pot over here. So if the output tries to go down, what's going to happen? It's going to cause this output to try to go down, right? And what's the guy going to do? It's going to raise the output back up to maintain a constant output. So this is an LM317, great guy. Like I said, I'm doing something to get more current out of it. I'll show y'all the schematic on mine. It's not hard to do. I've actually got this driving a big transistor or 2 big transistors to actually get a lot more current out of it than it's capable of doing. And I'll show you how to do that if you wanted to make a nice variable power supply.
So those symbols at the bottom and other symbols at the ground.
Yeah, this is chassis ground.
That's
So we have 3 symbols for chassis ground. This is usually a symbol for true earth ground, but it's also what they call chassis ground. But yeah, it's another symbol for ground.
that's it.
And this formula looks kind of hairy, but you don't really need to use that. What we do is there's almost no current flow into to make this thing work. So when we calculate this divider right here, basically we do it on our pot, you know. So if I had a 1/4 watt pot, then we would calculate the minimum and maximum currents that we would put through it, right? You understand what I'm saying? So if I adjust this all the way down to 0, then the amount of current flow we would get would be the size of this resistor flowing through the pot, right? Does that make sense? And we want to make sure we don't exceed the wattage rating on the pot that we put down there. And that's about it. So let's look at the, y'all bring up, did I put the trainer power supplies on there? Is it on Blackboard? I tried to do it as a PowerPoint somewhere, but I can't remember if I put it on this class or not. And if I don't, then the one I have was actually scanned out of the book that came with the little power supply. This trainer that we have, I can't remember what it costs, but it's less than $200 if you buy it in kit form. And it'll come with all your parts, and you got to solder it all together and put it together. Yeah, the trainer. It's a good deal. I mean, it's compared to what we were paying for the Heath trainers that we were using. I see what this one is. I believe this is not what I'm looking for. No. Huh? We take it at the end of class. We take it at the end of the class. I thought we went over that the first night. Normally what we do is we give our tests at the end of class, so that way if you get too early, you can do what? Yeah. And if we gave it at the first of class, we can't afford to take off the whole class for a test. So what we would do is we gave it first of class, then we would be doing this kind of stuff at the end of class. Unfortunately, we can't. This is not an English class where most of the time when you have a test night, what do they do? Yeah. Well, you'll do it here. Now, what's nice about this trainer, you can use it for both analog and digital, which is pretty neat. So used to, when we're doing the other trainers, they were like about $400 a piece, and you had an analog trainer and a digital trainer. This guy right here was cost less, and it's actually both trainers in one. So this is the power supply section. Let's get to the power supply section. So here's the power supply section. So we have a multi-winding transformer. Here's a fuse. They transform. And it's. I usually like to fuse the primary because that way you try to protect the transformer. But this is a multi-winding transformer.
You ever run across situations with both primary and then the secondary are also fused?
Yeah, I have, but I don't know. I'll give you all the procedure. It's in the NEC National Electrical Code book that shows you how to calculate the fuse for the secondary and the primary. But you actually overfuse them because of a lot of things that go on, and plus things that happen on the power lines and stuff like that. but here's a 7812. What's the 7812? That's a positive 12 volt regulator. Here's a 7912. It's a what? This looks like this is a full wave bridge, but they're using it as a full wave center tap. See the center. If this was a full wave bridge, this center tap would not be connected to common. So can y'all see that? So this is a full wave center tap oops, I didn't want to do that. These are two full wave center tap transformers. Oh, dang it. I can't draw on it, but I can show you. If you follow this over here, notice it goes to this and this and this and this. This is two anodes right here. This is two cathodes. So these right here feed your positive supply. These two right here feed your negative supply. So these are two center tap, full wave center tap power supplies. Y'all understand that? Because this power supply is using these two diodes. This power supply is using these two diodes. So anytime you see this grounded center tap, that is a full wave center tap. We can't have the center tap on the transformer side if it's a full wave bridge. So over here, this is a full wave bridge. Where's the common at? The common's on the other side of the diodes, right? You understand? Here, where's the common at? It's on the transformer. So even though this is a bridge rectifier, it's an integrated bridge rectifier, but they're using the two sets of diodes as a full wave center tap. And what that does, and I see this do a lot because we can have one bridge and have both a negative and positive supply off of one bridge rectifier. Here's my filter. Here's my input filter for the regulator. Here's my output filter for the regulator. Here's the little LED that comes on when you turn your trainer on, and this is the little terminal plug for plus 12 ohms. Same thing down here. And notice the LEDs turn the other direction, right? Notice here we just blew up this capacitor right here, so this symbol's drawn wrong. Why is that? It's polarized, yeah. Well, we polarize capacitors, especially in DC circuits, because the more farads you get, and I told you how we change the capacitance. We can either bring the plates closer together, but the closer we get to get them together, the lower the voltage we can charge them up to. So when they start dealing with higher working voltages, that means the plates have to get further apart. Well, to get the same capacitance, the other way we do it is we make the plates bigger. Okay, so what they do is they polarize the plates. So we have one plate that's designed to hold a positive charge, one that's designed to hold a negative charge, the metals they use inside the things. So that means now if you flip them around, it acts like a resistor. So if you flip it around, it acts like a resistor. Current is going to flow through it. It's going to drop a voltage, and it's going to get hot real fast. And what's it going to do? It's going to blow up on it, especially in power supplies, because the only thing you got limiting the current flow into these capacitors is the DC resistance of those transformers right there. So if you hook on a power supply, if you put that polarized capacitor in there backwards, it will blow up on them. And an amplifier, you got so many resistors that's protecting the capacitor. You just won't get gains, and it'll be all screwed up. The amplifier won't do. But usually in an amplifier, it's not going to hurt the capacitor. It'll hurt everything else. But in a power supply, it will blow up. We saw this. The video's up there. If you want to watch it again, I put it on the blackboard. And hooking them in backwards actually blew them up worse than what? Over voltages, exceeding the breaking voltages. So here's a 7805, and here's an LM. They're using an LM330. No, where's their yeah, they're using an LM337. This is an LM317, and this is an LM337. This is the LM317 is for our what? Positive supply, and the LM337 is for the what? The negative supply. Here's the pod over here. These are actually connected. Here's the output. Where's the output terminal at? Where's the output terminal at on the schematic? Oh, right here, TB, right here. And then here's the output. Here's the voltage divider, and here's your pot wired as a rheostat. So as soon as you tie as soon as you take the wiper of the pod and connect it to one side, it acts like a rheostat. So what's the difference between a rheostat and a pot? What do we use pots for? Voltage. And rheostats for current. So if we vary the current here, we change the drop there. So these are pots wired as rheostats. And you're going to see that a lot. So you can actually make a pot serve two functions. So these are the power supplies on the trainer. This is a high current power supply. It's got its own. This is a 5 volt. So the 5 volt. This is a 5 volt 5 amp regulator right here. And this is the guy that we're burning up left and right. It's actually a 78H05. And so we're replacing them with another one that seems to be doing okay. So there they are. I mean, very simple, we would have to look and see. In fact, it's on the transformer of what these different supplies are rated at. I mean, the actual output here. So this is probably a 12.65. Well, we're getting 12 volts out of that. So this is probably a 12. This would have to be more than 12.6, right? Yeah, this is 32 volt. So this is the 32 volt center tap transformer, giving us our plus and minus. This is rated at a quarter amp. This guy is rated at 1. This guy is rated at. It says this guy here is rated at it's 9 volts, and it says 1 amp. But I think the trainer says 5 amps. I have to look at that. And we refer to these as linear power supplies. And you'll run into these a lot. The other type of power supply we have is what we call a switching power supply. And these are very, very popular in like computers use them a lot. All your cell phone chargers use switch mode power supplies. This guy makes it simpler than it is, but this is a good video. learn about. What? Yeah, he does. And of course, we don't have time. We have 2 electronics courses, we don't have enough time to get in op amps in this class. We have an advanced electronic course that should be in your list of electives if you decide to take that. And we spend a lot of time with these devices called op amps. But you hear what he said? It says this output will. What the op amp is trying to do is trying to keep these 2 inputs equal. So what it does is that this one comes from a feedback, and then we put in a reference. And then this guy's going to drive this output to make this input equal. Does that make sense? And it's a really neat device. These op amps are really, really sweet. So what he's saying is that, okay, we're putting 5 volts in right here, and it's going to try to make this be at what? 5 volts. If the output tries to go down, then it don't match, and the output will go up to get that feedback. And what he said is the only difference between this and the LM317 is that the voltage divider is outside. Okay, here the voltage divider is inside. Now he made it very, very simple. If you ever look at a schematic of a 7405, there is a lot more to it than what he said. But he'll have a device called a Zener that we're looking at later on. But what we do on a switch mode power supply is right. So what do we do on a regular? First of all, on a linear power supply, normally what we do is we plug it in the wall, then we have a transformer. Okay, and what does the transformer do for us? Step it up or step down depending on what we need on the output, right? You understand that? Then we do what? Then we rectify it, then we filter it, then we regulate. What we do on a switch mode power supply is we bring it in, we don't have a transformer. The transformer's not first. We bring it in and we rectify it right off the bat. Then we filter it. Then we run it into a switch circuit. Then we run it into a transformer. But the transformer is controlled by a switch circuit. So we have a switch circuit right here that's coming in and oscillating the transformer. And the transformer does the same function. But what determines how much we get through a transformer? I think we talked about that, induced voltage. We talked about that, about what determines how much voltage we would induce into another conductor. We talked about that in a transformer. So to induce a voltage into another winding, what do we need? We need a magnetic field, we need a conductor, and we need motion. What determines the amount? The strength of the field, the number of loops, and the speed of the motion. So what happens if we increase the speed of the motion, instead of using 60 cycles from out of our power, let's say we use 100 kilohertz. now our transformers are going to be little old tiny things. I mean, little old tiny things, because they become so much more efficient because the frequency's gone up so high, so it can pass more energy with less windings, right? Does that make sense? So you look at a transformer inside a switching power supply, and it's a little old tiny thing, because it's switching at 100 kilohertz. And then we'll filter it, and then we'll regulate it. And what we use, the main filter is a device that we call a inductor. You know. So what I've done is I've kind of played around with this. So y'all come up here and I'll show y'all this power supply up here. But it'd be better if you see it. Now what I'm doing is I'm faking my oscillator. So this is what we would get out of the oscillator. So we come in and do what? We rectify it, filter it, and oscillate. Oscillate means we take a DC waveform and convert it into some type of pulsing. But what we're doing with our transistors is the elements that are working, they're either all the way on or all the way off. How much power does a closed switch produce? None, because it has no R. So you might have 10 amps worth of I, but its power is equal to V times I. So it means if I turn my transistor on all the way, we call it saturation, it's still going to drop a voltage, but it's not going to be hardly any. And then we turn it off. How much power does an open switch display? Now we got a lot of voltage, but we have what? No current. So what we're doing on these transistors, we either turn them wide open or we turn them off. So it would be like me taking a switch and doing one. Turn off, turn on, turn off, turn on, turn off, turn on. And the switch don't get hot at all. Now these guys are going to get warm because they are not switches, they are transistors, so they will always drop voltage. They just don't drop very much. So we'll still have to heat sink them and stuff like that. So what I'm doing is I'm using this to simulate the output of my oscillator. It puts out what we call a square waveform. Now this is my DC. So this is an inductor filter. We don't have time to teach inductors, but all an inductor is just a bunch of liquid wire. And what it does, inductors hate change. They hate change. So what we do is, if it sees a change, and what it tries to do is it tries to block the change. And then when the change goes away, it will discharge into the unit. So this is my output voltage right here. This is what I'm inputting into that inductor. This is what I'm outputting. So here's channel 2 right here. This is 0. Here's my output filter right there. So my filter's only having to run. I'm putting what in? I'm putting 119 kilohertz in that thing. So how long does the filter have to maintain the output? None. So that means we'll have one big old filter capacitor on the input side, on the input rectifier, and then the output filters will be little tiny. Transformers are going to be, if we use a transformer at all. We don't have to use a transformer. We'll just use a transformer if I need multiple voltages out. If I need one voltage out, we don't need a transformer. And watch what I'm doing. So I'm not going to change the frequency. What I'm going to do is change what we call the duty cycle. The duty cycle is the width of the pulse. So notice when I make the pulse, I'm not going to change the frequency. If you want to, so if you look at the two negative edges right here, you'll see them now removed. But what I'm going to do is I'm going to change the width of the pulse. So we call it pulse width modulation. And watch what happens to the output. I'm not going to change the input voltage at all. So here's the duty cycle. So if I use a smaller duty cycle, my output voltage goes down. If I use a bigger duty cycle, my output voltage goes up. So all we have to do, my regulator, it looks at the output, and if the output tries to go down, it increases the width of the pulses. If the output tries to go up, it decreases the width of the pulses, and that's the way these things are. But why they're so good in cell phone chargers and stuff like that, they're so efficient that I can come up, and this guy right here is this guy right here outputs 20 volts at 3.5 amps. And look at the size of it. Don't get real hot at all, because those transistors are either on or they're off. When they're on, they're dropping very little voltage, even though current flows through them and it does get warm. But when they're off, they're not doing anything. A linear power supply, your regulator is always, it's going to have to drop the difference between the unregulated and the regulated. So we get into those power supplies, they're going to be, the transistors are going to be bigger. We're going to have more what he calls series paths. We're going to have to heat sink them. But they're real easy to design. These guys right here are not easy to design, no matter what he said. And they're basically real hard to troubleshoot. Because you got to start that oscillator up, so it's got a feedback circuit in there. But what you'll find out is that usually, like these, you can't fix these because they're sealed, right? If you take this thing apart, it's all sealed up. I mean, you would be spending hours just trying to get the goop off the thing so you can make measurements on it. You know, if you think how much money you make an hour at your job, you know, of course, if you got the time, that's fine. They're hard to troubleshoot because of the feedback circuit. Design is not a big deal because you can buy the switching mode regulator chips. Then all you do is add a few external components, so they're not hard to combine. The biggest problem we have is they generate tons of electrical noise. So what happens when these guys here turn on, then we're loading our input power. When they turn off, we're not loading our input power. So what happens is they generate a lot of line noise. They screw up the power factor of the system. So there's a little more to it. They got to really, really filter the input. So this will come through input filters. A good one will come through input filters. But look at the charger for your cell phone. We call them little bricks, right? Little tiny things. But you know, if you look at the current output, it's amazing because they're what? They're switching power supplies. Now they get warm, but they don't get hot. And why? Because those active elements are either what? On or off. And of course, what happens when that thing goes out? You throw it down. But, that's the switching power supply. Ain't that neat though? I mean, it's real weird. So this is on this side. So this scope probe is right here. This is the inductor. Here's my filter. And then this is on the output. And you can see the switching noise. I'm going to take so that's the filter out. So you get that switching noise on the output. But it don't take hardly anything at all to do what? Got to clean it up. And that's right there is. So what did I do with it? Didn't I bring that power supply out here? Yeah. So, like I said, you don't even have to have a transformer. If I look at the input, so what we used to have on the old power supply is that, like this one right here, so this you got a transformer. So this got a switch, so I have to switch it between 115 and 240. So that would be over here would be 115 over in the middle switch over to 240. And that's because it's got a transformer. Don't have a transformer in it like these guys. This guy I can put anything between 100 to 240 volts, 50 or 60 volts. So there's no transformer, right? This one we have a switch on it. This is a switch to the power supply. This is like a 450 watt power supply. Here's your transformer right here. Here's your input capacity. Here's your grid rectifier. So this is taking out power. This is the input filter. I use conductors in the input filter also. You want to get over on the output side. This guy here puts out plus or minus 12, puts out plus 5, puts out minus, puts out a plus 3.4. This guy here, plus 5, so 30 minutes. Side. These are your, so this is the input filter. You want to get over on the output side. This is the input filter. You want to get over on the output side. This guy here puts out plus 5, puts out minus, puts out a plus 3.4. This guy here, plus 5, puts out 30 minutes. Side. These are your, probably switch transitions right here. Why are you? Wow. AC, take AC and then how they take AC and how they another source charge magnetic where they pass charge start charge stand time constant for conductor all time constant for that R times C conductor bigger resistor you have fast called cause and cause.
So transistor basically two vectors, two
Transistor.
transform. I'm sorry.
Yeah, a transformer is two inductors together, so so what are inductors used for? They're used for transformer. But what we do is we have them so close together that this thing generates a magnetic field it couples into the second. And that's why if you measure the resistance of them, you'll measure 15 ohms. Big transformer, high current transformer, maybe run 1 or 2 ohms. So if it don't get its opposition from R, it gets its opposition to something called A. It uses you put DC on the transformer, it's going to because it's not, it's designed, it gets its opposition from that chain, from that chain. You get the opposition. But we use meters to check to see if you got open line. If you've got good transformers, you can tell if they're good. You can tell the ratio too, just by the resistance ratio of the output and the input. But if you got a good one sitting there, you can measure the resistance of the primary and resistance of the secondary. And then if you've got that written down, you can check open, you can check for shorted windings. If you got shorted windings, the resistance is going to be what? It's going to be less. You got open windings, of course. Okay, go. Yeah, so we do that all the time in most of our labs to check those transformers over there. Yeah, so this is the switching power supply that's being this often. More and more we're going to be switching power supplies unless you're in audio. If you're in audio, I'll draw there on linear power supplies because they're a lot smoother and cleaner than have all that switching. So type of communication, transmission, or anything like that, I'm using power supply. Computers, switching power supplies, develop their efficient, there's so much more efficient, which means you get more watts out of the other side. So we can start making these strings small, get more watts out of the other side. The problem we have is they're very, very noisy. So they take a lot of distance. AC and also motor control, we talk about something called power factor. What happens in AC circuits is these devices are called phase shift between the voltage and the current. In your power supply, these guys are recorded. What they unload and what they unload. Notorious about having a very full power factor. The more expensive one with the power factor breaking circuit in there, really filtered into nice. Your old switching power supplies, they were off. Phase shift and racing circuit is something. What you end up creating something called apparent power. Which means that's how the computers are doing. We have real power, the actual computer. Apparent power is always greater than real power. You can't just measure it. So if you go over there on the output, you measure V times I on the AC circuit, you calculate what's called apparent power. You wouldn't know what the real power was unless you could measure that ratio. You call it power factor. AC or one type of power pack. So if you ever look at the transformer never rated in watts. An AC generator are not rated in watts. Cars, people their power. They're rated in something called capacity. So you ever see VA or AVA, that's apparent power. And you ever see watts, that's true power. Are we okay? For this, we'll start test at 7 o'clock and go ahead and take a break. You go 2 hours to take it. By the way, I'm going to give you all a different corner sheet for the night test. It's just going to have power supply.
Something, electric, I don't see it.
Let me tell you what I have to do to get links. I have to record them on screen. Then I have to upload them. Then I go to YouTube and actually share them, come back and embed them inside. It takes probably an hour and a half to upload a lecture.
Oh, no, the lecture, I'm looking at the slide, the PowerPoint, I won't see it.
Okay. I thought you were talking about the lecture.
No.
Yeah, so these lectures are not going to pop up like on integrity. They all want to pop up instantly. These lectures.
The only slides I saw is in chapter 3 and 4 combined, and then it's only.
Well, the slides are not given in chapters; they're given in topics, because the chapters change from book to book, but the topics that we teach don't change from book to book. So there should be this one. So I'll see what's up there. So course content. Yeah, these are not going to be in chapters. These are alternating currents, semiconductor diodes. Okay. That's what we're talking about. Lecture sides, P-N junction, diode characteristics, troubleshooting rectifiers, power supplies, and regulators. That's the one we just got through looking at.
For some reason, I just tried to open it on this computer. Open it.
Yeah, so this is the one we just got through looking at.
There was another file. PowerPoint. They don't sell.
Well, it's not important that they don't open here because I'm putting them up on the board. What's important if they don't open at home.
Yeah.
Okay, understand? So it's not important, but they're there, right? Understand? So you said they wasn't there. You didn't tell me they would. You didn't say it wasn't this way.
Yeah, I couldn't see it.
So make sure you use Chrome. Don't use Explorer. If you're using Explorer, Chrome don't even support XP anymore. But it's better than using Internet Explorer. Internet Explorer, last version they had for this was 8, and I think we're on 11 or 12 now. So that's why we got Chrome installed on all these computers. So it's there. So what you need to do is check it out at home. I can understand why y'all want to look at them for them here. And honest to goodness, I've been tempted to go and turn every one of these computers off while I'm lecturing. I really. But listen to me,
Oh yeah, I got you.
because you get people, they'll be back on their computer and they'll be over there playing solitaire. Or they'll be looking at that thing and not looking up here. And sometimes these things don't match because I have to upload all these too. So if I go in my office before I come here and make a change because I see something wrong, or if I add something, they're not gonna be on the PowerPoint slide. So it would be nice if I made a change in there. So to get these up here, you wouldn't believe what it takes to get these up here. So I mean, and the recorded lectures, they are even worse. So and I put them up there as a convenience. So like I said, I would rather y'all listen to me and look at the slides and let me mark up here than try to follow the slides back there.
Yeah, that's what.
But if it don't do it from your computer at home, you need to let me know. Just because it don't work here, that's no big deal. And like I said, it wouldn't surprise me. We did, they put, when we was up at that training session up at Mercedes, I recorded all that.